Welcome, everyone. Get ready because today we are diving headfirst into the invisible architecture of our universe. In this explainer, we're going to unpack the foundational forces that govern literally everything around us. I'm talking about forces you can't see, but that completely dictate how matter interacts at the absolute most fundamental level. We're looking at electric charges and electric fields. So if you've ever found yourself wondering what really happens when things attract or repel, or how the basic building blocks of nature somehow communicate across empty space, you are definitely in the right place. Let's get into it. Here is our roadmap for today. First, the fundamentals of electric charge. Second, Coulomb's law and calculating force. Third, visualizing the electric field. Fourth, the power of electric dipoles. And number 5, electric flux and Gauss's law. All right, let's kick things off with Section 1, the fundamentals of electric charge. To really wrap your head around electricity, you got to start at the absolute source. Electric charge is this intrinsic, pure property of matter. It's honestly just like mass. It's a fundamental characteristic of the particles making up our universe. And when an object becomes charged, it is entirely due to the transfer of electrons. See, atoms are naturally neutral, right? They've got an equal number of positive protons and negative electrons. But when external forces, like, say, friction, are applied, electrons can actually get stripped from one material and transferred over to another. That imbalance right there is exactly what gives a body the ability to exert an electrostatic force. Now here's something kind of wild. This transfer of electrons actually has a physical consequence. When an object loses electrons, sure, it gains a positive charge because it now has more protons, but it also literally loses mass because electrons, as unimaginably tiny as they are, do have mass. Conversely, when an object takes on an excess of electrons and becomes negatively charged, its physical mass actually increases. It's a microscopic change, obviously, but it is just a fascinating reality of physics that charging an object actually alters its physical weight. But nature has some pretty strict rules about how this works. This incredibly tiny number, 1.6 times 10 to the power of negative 19 coulombs, is the exact charge of a single electron. And this brings us to a massively important rule called the quantization of charge. Basically, it means charge can only ever be transferred in fixed, unbroken packets. You cannot transfer half an electron. Any charge on any body in the entire universe has to be a complete integer multiple of this exact specific number. No exceptions. So how exactly does a totally uncharged, neutral body get this charge in the first place? Well, there are 3 specific ways. First up is friction, literally just rubbing 2 objects together, physically scraping electrons off one and dumping them onto the other. Second is conduction, which is when there's direct physical contact between a charged body and a neutral one, letting the charge just flow right across and share itself. And third is this brilliant phenomenon called induction. This is where a charged body is brought near a neutral one without ever touching it. It forces the charges inside the neutral body to separate and reorganize themselves purely through that invisible electrostatic force. Moving right along to Section 2, Coulomb's law, calculating force. Okay, so we know from basic everyday observation that similar charges repel and opposites attract. But physics is about precision, right? It's not just about noticing things happen. Exactly how do we calculate the strength of this invisible push and pull between them? Enter Coulomb's law, named after the famous 18th century French physicist. This elegantly simple formula tells us that the force is directly proportional to the multiplied magnitude of the 2 charges divided by the square of the distance between them. And this beautifully illustrates a universal truth. Distance is the ultimate killer of the electrostatic force. Because distance is squared right there in the denominator, if you just double the distance between 2 charges, the invisible force between them doesn't just get cut in half, it plummets to a quarter of its original strength. That brings us to Section 3, visualizing the electric field. You see, a charge doesn't just exert force in a single straight line. It commands an entire 3-dimensional web of influence all around itself. We call this the electric field. You can think of it as the charge's absolute territory. If any other charge dares to enter this specific region, it is going to instantly experience an attractive or repulsive force. So to really understand this mathematically, and to be able to visualize it, physicists came up with the concept of electric field lines. And these electric field lines follow a set of definitive, unbreakable rules. First, they always start at a positive charge and end at a negative one. Second, they are smooth, continuous curves that never just randomly break off. Third, they never form closed loops, meaning they don't circle back on themselves.
Fourth, they always exit or enter a conductor at exactly a 90-degree perpendicular angle. But the absolute most important rule, they never ever intersect. Think about it. If two field lines crossed, it would mathematically mean a charge placed at that intersection would be pushed in two completely different directions at the exact same time. And that is physically impossible.
Let's jump into Section 4, the power of electric dipoles. So, an electric dipole is simply a pair of charges, one positive, one negative, that are perfectly equal in magnitude, but separated by a small specific distance. Now you might be thinking, well, one is plus and one is minus, so wouldn't they just cancel each other out completely? And yeah, the total net charge is technically zero, but because there's physical space separating them, their individual electric fields don't perfectly cancel. Instead, they interact to create this highly unique and really powerful electric field of their own. This specific geometry is literally the foundational architecture of polar molecules, like the water molecules that make all life on Earth possible. What's really fascinating here is how the field strength behaves depending on exactly where you measure it. If you measure the electric field perfectly aligned on the axis running straight through the two charges, what we call the axial point, it's exactly twice as powerful as the field measured on the perpendicular equator, or the equatorial point. The dipole's influence is incredibly, aggressively directional. So what happens if we take this rigid little dipole and drop it right into an external uniform electric field? Well, the external field is going to pull the positive end one way and push the negative end the exact opposite way. This generates torque, actually forcing the dipole to physically rotate. The amount of rotation, the torque, depends purely on its alignment angle with the external field. It's perfectly modeled by the equation torque equals the dipole moment times the electric field times the sine of the angle between them. It's basically nature's own invisible motor. Finally, we arrive at Section 5, electric flux and Gauss's law. Up until now, we've really just been looking at single-point charges, or these tiny little dipoles. But what about the real world? How in the world do we calculate the electric fields for giant continuous systems of charge? Trying to use simple Coulomb's law to calculate the field of a massive charged sheet or an infinitely long wire would require incredibly tedious, practically impossible math, where you'd have to add up an infinite number of tiny point charges. We desperately need a shortcut. But before I give you that shortcut, we gotta understand electric flux. Flux is essentially just the total measurement of electric field lines that are piercing perpendicularly through a given surface area. Imagine you're holding a hula hoop outside in a rainstorm. The amount of rain falling directly through that open space, that's your flux. If you tilt the hoop, less rain goes through. If you hold it perfectly sideways, zero rain goes through. Electric flux works the exact same way, just measuring how much electric field is penetrating a specific area. And this brilliantly sets up that ultimate physics shortcut I promised, Gauss's law. This law dictates that the total complex electric flux passing out of any closed three-dimensional surface, just imagine an invisible bubble, is elegantly simple. It is equal to exactly the total charge trapped inside that bubble, divided by a constant known as the electrical permittivity of free space. It literally doesn't matter what shape the bubble is, or where the charges are randomly placed inside it. You just take the inside charge, divide by the constant, and boom, you have your total flux. By using Gauss's law, physicists can easily calculate the electric field of massive, complex shapes. It's an incredible cheat sheet. For an infinitely long charged wire, the electric field weakens as you move away, inversely proportional to the distance. For a spherical shell, the field outside acts just like a point charge. But amazingly, the field anywhere inside that hollow shell is absolutely zero. But look at the infinite plane sheet. Because of its massive geometry, its electric field formula completely drops the distance variable entirely. The electric field projecting off an infinitely large charged plane literally never weakens, no matter how far away you get from it. How cool is that? We've journeyed all the way from the microscopic transfer of a single electron's charge up to the vast, distance-defying electric fields of infinite planes. These invisible electrostatic rules absolutely dictate the architecture of everything around you. They hold together the molecules in your body, and they drive the technology you're using right this second. So as we wrap up this explainer, I want to leave you with this thought. If these highly structured, perfectly mathematical, invisible fields are constantly interacting, pushing, and pulling all around you without you ever even noticing, what other unseen forces are shaping your reality right now? Thank you so much for joining me. Keep learning, and I'll catch you on the next explainer.